hopefully it should be somebody without disciplinary problems, walls. And, okay, please, you will talk about heart.
Yes. First of all, let me thank the organizers for the kind invitation, after the Beltrami medal, it's going to be quite difficult to restart, but I will try to be as multidisciplinary as possible, talking about frequency ablation, which is a specific procedure which needs our support. First of all, probably most of you don't know Campus Bio-Medico in Rome is over here, okay, just outside the big highway circle in Rome. We are multidisciplinary by definition, and my lab is linear physics and mathematical modeling. So already by the name of the group, you may imagine the different activities we bring on. By the way, today I'm going to talk to you about a specific problem, which is radiofrequency ablation, and in particular a novel computational framework based on advanced constitutive modeling of the heart, particularly of the myocardium, focusing on the microstructure, because as I'm going to tell you shortly, for this particular application, the microstructure of the heart was discarded. In fact, if you know something about this procedure, it is very much used when we suffer of atrial fibrillation or ventricular fibrillation. This is a very diffuse disease, expected to be one of the leading cause of death as well in the previous talk. And one of the solution strategy that is used in the clinics is the usage of radiofrequency catheter ablation, which basically burns some part of the endocardium, okay, such that eventually these complex waves of action potential coming into the heart are stopped and arrhythmias do not sustain anymore. Of course, there are many drawbacks of this procedure, and so optimization is necessary. Basically, you have a radiofrequency generator, a dispersive electrode in order to make the circuit close. The catheter enters into the cardiovascular system, reaches the heart, enters into the chambers, and you generate radiofrequency from here, and you burn the tissue, okay? This is what's going on. So as you can imagine, the heart is a very complex system, as basically all know, but in particular it is a multi-layer material composed by several fiber structures. In particular, the myocardium, which is the thickest part of the organ responsible for the contractility, is arranged in a fiber-like structure, and the micro orientation of these fibers rotates on the depth, along the depth of the ventricular wall. Here you don't see, but basically it goes from -60 to +60 degrees usually. Okay, this is an average value, and this is called rotational anisotropy in the cardiac literature. Of course, this is a transverse isotropic material with reinforced fibers and so on, but this is the name they call it. Okay, so this particular feature was absent in the modeling of this application, and in fact what we're gonna discuss today is the generalized constitutive framework accounting for the microstructure and the other multi-field couplings, also at different length and time scales. Okay, to be more precise, we involve 4 different physical mechanisms. First one is mechanics, because the electrode must be pushed on the endocardium such that the contact surface is as much as possible. Okay, so there is a contact mechanic problem. Then you have a radiofrequency source. The radiofrequency source accelerates the kinetic energy of the water molecules, and we generate heat. Okay, so different scales as well. And there is a big problem of heat transfer in biological media. It's very, very complex. And then the aim is to kill the cells, okay, but in a controlled manner, so not too much. Okay, so we have to deal with all these phenomena, and let's start via an engineering approach as simple as possible. Let's take a computational domain which has a rectangular slab with the physical dimensions of the order of a ventricle, 8 by 8 centimeters, 2 centimeters in thickness, and impose this rotational anisotropy in terms of myocardial fibers. Okay, this is going to be used for different physics: thermal conduction, electrical conduction, mechanical reinforcement. This is the electrode. So the electrode is 2.3 millimeters, so much smaller than the computational domain. So boundary conditions are very important, well tuned, as I'm going to discuss, but they are far away from the electrical surface. Even though we are talking about electrical currents, so if you do not compensate for electrical currents, you do not recover any physical behavior. Okay, everything is framed in continuum mechanics. I can skip basically this slide, but we are considering finite elasticity, a continuum assumption, and invariant-based strain energy functions. In particular, we have also to consider the anisotropic part of the story. In terms of kinematics, we assume the classical multiplicative decomposition of the deformation gradient, and in this particular case, we have to consider the thermal contribution. Okay, so we have an additional splitting of the deformation gradient. In a first approach, the thermal deformation gradient Ft is proportional to the delta T, where T0 is the reference body temperature, which is 37 degrees, okay? But even though we have incompressibility, because it's a material full of water, so the incompressibility constraint is a very good approximation, the thermal part is going to induce residual volumetric deformations because of this map, okay? Now, in terms of boundary conditions, we have to be very careful. The mechanical ones are quite simple in the sense that we assume that the slab is laying down on our experimental setup. So fixed constraint over here and traction constraint here. This traction constraint mimics the force that is applied and is controlled on the catheter. Okay, this is one of the controlling parameters in order to recover the experimental data. In terms of strain energy density, this is the story. Okay, basically everything is coupled with everything else, because we have that the stiffness-like parameters in the Mooney-Rivlin model that we use in a hyperelastic framework depend on temperature. Okay? Then we have the thermomechanical strain energy density, which depends on a multi-scale parameter Xi, which is linked, as I'm going to discuss shortly, to the cell death model. Okay, so it's a multi-scale coupling. And we introduce a damage variable into the anisotropic contribution of the energy, because when we kill the cells disaggregate, so they do not form anymore, they don't sustain anymore myocardial fibers. Okay, this is the assumption. Of course, it's a phenomenological assumption, but it turns out to be quite reasonable. Okay, from the electrical point of view, we assume electrical current here entering at the electrode surface. The dispersive electrode is assumed on this surface over here with reference zero potential, while on the other boundaries we assume zero current. Okay? It's very important here to add an additional constraint to the Maxwell equations. Not only writing Maxwell equation in the reference configuration with the pullback because the material deforms, but it's really critical to force the overall power dissipated to be exactly at the level that the machine delivers, because the machine delivers a certain amount of power that is tuned by the medical doctors. 60 watt, okay, that's going to be tuned by the electronics inside, and if you do not impose this constraint into your equation, you do not recover the correct dissipation into the tissue. This is really critical. Now, from the heat transfer point of view, again, boundary conditions are very critical. The internal surface is assumed to be 37 degrees as the other two, while the endocardium is wet by the blood. Okay, there is blood going on, so convective boundary conditions have to be used. And also at the electrode surface, there is a saline solution that is released by the electrode itself in order to have a local cooling down. So another convective boundary condition is necessary. Okay? I'm going to show you how important are these two boundary conditions. And in terms of heat transfer model, we assume a classical Fourier type equation in the reference configuration because of the deformability of the domain. We have three source terms. The first one is the metabolic contribution of the tissue, which is a constant value according to the time scale. Then there is the perfusion term, which depends on the blood vessels inside the ventricular wall, and this is proportional to the delta T, so the difference of the current temperature versus the blood temperature. Is tuned by WB. This is called the this is the proportional coefficient. And finally, QS is due to the electromagnetic source. So this is a Joule heating effect, so proportional to the square of the electric field, which is generated by the radiofrequency source and is solved in the previous setup, okay, in the previous Maxwell equation.
So the effect of the heating is a volumetric thing. It's being modeled as a volumetric source, not as a flux, not as a heat flux at the surface.
No, because we solve Maxwell equation in the domain. We have the electric field everywhere. And once we have the electric field at this point, we compute locally the source of temperature, so of heat locally. Okay.
And then what were the boundary conditions on the side for the mechanics part?
Zero
deformation at the bottom.
Yeah, these are free boundary conditions. So the tissue can deform. But these are so large with respect to the size of the electrode that from the mechanical point of view are negligible, not for the others, especially for the Maxwell equation. Okay, everything. Yeah, this is just a section of the slab. The thermal conductivity is assumed to be anisotropic, as told before.
Sorry, there's no convective transport, like in the heat equation, there's no convection part because of the interstitial fluid.
Not in this case. Not in this case. I'm going to discuss later on an improved version. Okay. Now it turns out that here we have heat capacity. Okay. Now this heat capacity usually is assumed constant, but as you can see over here, it is a function of the mechanical state of the system and the thermal state of the system. In fact, the most general definition of heat capacity comes from the second derivative of the thermoelastic strain energy density. Okay? And if you make this computation, you have a constant heat capacity, which is basically the reference value that we all know, plus an additional term which depends on the second derivative of this equation, right, of this strain energy density. Now here it is critical to understand that Once you choose a certain strain energy function for the thermoelastic problem, then also all the multi-scale couplings go inside its capacity as well. So this is a generalized version, okay, in which, of course, these are higher order terms other than the constant heat capacity. But we are talking about temperatures that can go up to 100 degrees. So we are not talking about plus or minus 1 degree, because we have to kill the cell, and the temperature has to raise up to 100 degrees. So this contribution close to 100 degrees is going to be really important, okay? Not negligible anymore.
This C?
I'm going to discuss now. What is Xi? Xi comes from the cellular death model. So we assume a 3-state cellular death model in which we have an alive state of the cells that can go in a vulnerable state if they are stressed by temperature. This state can be reversible, okay? But eventually, if temperature is too high or for longer times, cells die, and because of protein denaturation. Okay, so this is a quite simple kinetic model, but from this model you can derive a relative shrinkage of this protein, Xi, which enters into the strain energy thermoelastic function. Okay, so the coupling of the changing of the thermoelastic potential is also due to the local changing of the cell dynamics. And finally, in a first approximation, the stiffness parameters, the thermal conductivity and the electrical conductivity are going to change linearly with temperature. This is an assumption made in literature, even though we know that this is wrong for sure, because at some point, these functions have to saturate, right? Every function has to saturate in biomechanics in a sigmoidal function. Okay, but up to 100 degrees, it has been more or less tested experimentally that these linear approximations are reasonable. Of course, each tissue, each sample is going to change. We have biological variability, but this is an approximation. Yes?
I was wondering why you have to go up to 100 degrees, because, I mean, cells die at 42, 43.
Yeah, that's a critical question, of course. The first one is because the medical doctor wants to be sure that they kill the cells. First one. The second one is because of the treatment itself is blind. I mean, they may know they have perfect contact and so on. The therapeutic guidelines say that you cannot apply more than 60 watt for 60 seconds or something like that. But this is because it depends on the subject. Eventually, they try to avoid 100 degrees because then you have a phase change of the material. You have a totally exactly. There are accelerations actually, but still in this range of temperatures, many phenomena arise. In any case, we stop the modeling up to 100 degrees exactly to avoid the phase change, because then a different modeling constitutive model has to enter inside. But again, from the blood perfusion point of view, there is a sudden drop of perfusion once the number of cells is below a certain threshold of alive cells. So this W coefficient is going to drop dramatically if the number of cells is going to reduce. Okay, so a very complex model. Everything is coupled with everything else. We have to set up a computational framework robust enough to deal with all this coupling without entering into the details. Of course, you can select the protocol, meaning you define for the electrode, you define the power that you want to deliver, and so all the constraints that I was discussing before. We have to be sure that we have convergence from a numerical point of view, and this was one of the tests that we done. So all the variables have an error below 100%, sorry, 1%. So in the proximity of the electrode, of course, we have to make a much more better refinement of the mesh. And then we start testing different boundary conditions. Why eventually a Dirichlet or a Neumann boundary condition for the electrical problem could affect the system? Well, if you impose a Dirichlet boundary condition, you have a local concentration of the electric field at the corners, okay? But this turned out that is not evident from the experiments. So the most reasonable boundary condition is a Neumann one, because you have a continuity of the electrical flux. Very, very important convective boundary conditions for the thermal problem. Now here, you have no convection, you have convection only for the blood, and you have convection both for blood and for the saline solution. Now, these curves over here are the lesions created during the procedure. If you do not have any convection, you see that the lesion starts exactly on the endocardium. As soon as you switch on a convective term, the lesion changes a little bit, and if you have both, the lesion forms inside the tissue, not on the surface, okay? And actually, it turns out that this is the most realistic one from an experimental point of view. Of course, with time passing, the lesion is gonna go also on the endocardium. But if you have the saline irrigation and you have the lesion forms inside the thickness. And here is the full couple model. So you push the electrode, so you have an initial deformation of the tissue. You impose the procedure. Here there is the thermal map up to 80 degrees. And the surface is the 50 degrees lesion, which is the quantitative indicator usually adopted from the medical community. Now, what is critical here is the fact that you push, you start heating, and as soon as you start heating and temperature goes up to 50 degrees, the electrode comes back, because I'm pushing with a fixed force, but the tissue is stiffening. There is a stiffening procedure, and this is actually experienced by medical doctors. In fact, they push in different locations, they stay 30 seconds, they change location, and so on. Because the tissue changes its material properties, so it becomes stiffer. And once you go back and you remove the electrode, okay, this is for different forces.
So the stiffening is because the properties are temperature dependent?
Yes.
But don't the properties decrease? Doesn't stiffness decrease?
The increases.
Increases.
Yeah, it's like when we eat a steak.
Yeah,
if it's too much cooked, it's stiffer, right? That's exactly the procedure. So this is for different force levels, so it's consistent with all the different force levels. But because of the damage process that we have introduced in the anisotropic contribution, this is an interesting result of the study. So this is the residual state that we get after the procedure. So you have some part of the tissue that are contracted and some part that are extended because of this denaturation process of the proteins. And in fact, if you compare this micromechanical aspect from with the 50 degrees isothermal contour, basically you have shrinkage and expansion inside the 50 degrees isothermal contour. So inside this qualitative, if you say, estimator of the lesion, you have many, many different aspects. Okay. Finally, we also did some experiment. Sorry, yeah, sure.
Question: the ablated tissue remains in situ, it remains in place, or it's sunk?
No, the tissue stays is dead. So it's a different material basically, but stays there, absolutely, yes.
But with metabolic action, it is not removed later?
No,
remains there.
absolutely. I mean, it's a continuum. No. It stays there. I mean, it's like an infarct region, right? It stays there. In fact, one of the drawbacks of the procedure is that action potential waves, if the procedure is not well done, can eventually attach to these discontinuities of material properties. And in fact, many times, patients have to undergo twice or many times under this surgery.
It's difficult to kill cells in the heart of somebody.
In fact, that's why we had to go up to 100 degrees. Okay.
I mean, it is a difficult decision.
Well, it's very common, actually. It's a very common procedure, even though there are many drawbacks from this point of view. Yes, it's very, very common.
The tissue remains alive or not?
No, this tissue is dead. So you have a transition, a smooth transition from healthy tissue to dead tissue. There is a so-called border zone in which some cells are alive and most of fibrotic tissue is formed. And this border zone is the one responsible for the anchoring of the action potential waves and the onset again of arrhythmias, which are rotating spiral waves.
I think you mentioned this, but just to make sure, so the dead part affects the heat transfer, it affects the electric field,
Yes.
right?
Yeah.
In the model.
Yes. Yeah, because
it has different properties.
yes. Yes, so during this procedure, during this...
your thermal conductivity is changing during the time.
Yeah. During this procedure, over here, you have... okay. During seconds, the stiffness is changing, that's why the electron comes back. But also the thermal conductivity is changing and the electrical conductivity is changing. So everything is changing. From the experimental point of view, we try to make a step further. So eventually you can measure the thermal map on the endocardium, but what's happening inside, right? So with a collaboration in my institute, we made use of fiber Bragg sensors that are sensors that you can insert inside the thickness, and you can measure locally the thermal state in time. Okay, so we have a map, a spatio-temporal map of the temperature when you have an electrode delivering a certain frequency. This is the setup. Of course, this is not human, it's porcine heart tissue. And this is the kind of curves that you can measure. Now, up to 60, we can reach closer to the electrode 70 or 80 degrees, not 100. We avoided steam drops. But in order to recover these trends, we have to generalize the heat equation once again. So it's necessary, as mentioned before, to introduce an additional convective term, but also an additional time derivative of temperature, such that we make use of the dual phase lag model. This is basically because we have two time constants, tau t and tau q, and these two time constants are the ones that allow us to reproduce the average rising of temperature. In fact, you see, I mean, there was a lot of tuning here according to the thermal anisotropy, the electrical anisotropy, and so on. So without bothering about the stuff, this is the final result. Final result is in black you have the model, the dual phase lag model, and these are the experimental data. Okay, as you can see, it's very much nonlinear. If you only consider the Fourier problem, or you get the first part, or you get the stationary part, you don't get the two times. So it's mandatory to have both anisotropy, otherwise at a different thickness we do not recover the right value, and the dual phase lag model, or any higher order equation for the heat problem. Okay. Once you have a tuned model, you can make some predictability, okay, and these are the experimental space-time maps that we can measure, and this is what the model is able to reproduce. Of course, the model is always smoother, but the key point is that in the medical literature, they say isothermal contour 50 degrees is like a sphere. It is not. It is not. It is 6.6 millimeters by 3.8, 7.8 by 5. So it's an ellipsoid one lesion. And this is what the model is able more or less to reproduce. Of course, this comes from the complexity of the microstructure, the anisotropy, and all the couplings. If we do not have the cellular depth model, we do not recover the different dynamics. Okay, many open problems, still contact mechanics, how to design new materials, the interfaces, and so on. These are a couple of references and just an advertisement for anyone who's going to be interested. We're going to organize a second edition of the Advanced International School on Experiments, Modeling, and Simulations in Biomechanics and Mechanobiology in Rome next February. So please contact us because we are collecting many requests and we have a limited number of seats. So if PhD from your group or even younger postdoc are interested, just let me know. Thank you very much.